Hello everyone. Today I'll present BLens, contrastive captioning of binary functions using Ensemble Embedding. And this is a joint work with my colleagues from UniBV, LMU Munich, and MCML. And the project is fully open sourced, and it has earned all 3 artifact evaluation badges. So you can try it out, reproduce our results, or even compare it to your own methods. And let's get started. So first, let's start with an example. Picture this. You open a stripped binary IDA-Pro, and this is usually what you will see, a long list of functions with placeholder-like names. And these names tell you nothing about what the function actually does. So if you are a reverse engineer, you have to go function by function, read the assembly or pseudocode, and guess its purpose. It's slow and tedious, and for large binaries, it would be error-prone. And now imagine the opposite. The function names are explicit. Here we see names like scan and encrypt file. And without even reading the code, you are already thinking, this smells like ransomware. Then what happens if we use AI to generate function names automatically? So using DeepSeek, we analyzed this assembly code, and the model was prompted to suggest possible function names based on observed behavior. And here are its top guesses: recursive directory traversal and process file data. And these are reasonable guesses, but they miss the word encrypt. And without this word, these functions look like they belong to a harmless program. So that brings us to our first challenge. When predictions lack precision, they can be misleading, forcing reverse engineers to spend extra time correcting them. And to address this, we stick with learning-based methods. We train a specialized model to understand the semantics of binary code and then predict meaningful names. And this can greatly reduce the reverse engineering effort. Before introducing our method, let's first look at the baseline approaches for learning-based function name prediction. They generally fall into 2 categories: recommender-style approaches and translation-style approaches. So the first category is the recommender-style approach, and here represented by XFO. The idea is to treat function name prediction as a multi-label classification or recommendation problem, and each token in the function name is treated as an independent label. That means the model decides yes or no for each token, without considering the order or the context between tokens. So for example, the model may select the tokens to, int, and string, and a post-NLP step then orders them. But this ordering comes purely from natural language patterns, not the function semantics. And as a result, it may still produce string to int instead of the ground truth int to string. And that's our second challenge. Without grounding the ordering in the actual code, we risk losing important semantics. And the second category is the translator-style approach, such as SimLM, ASM Depictor, and HexT5. And these models treat function name prediction as a translation-like task. They model both context and word order, producing fluent and accurate names when the pattern is familiar, but they are sensitive to unseen name patterns under domain shift. So for example, in training, the model sees functions like print integer and into float, and in the test set, it faces a new but related function, print float. And the code is structurally similar, but the name pattern is new, so the model gravitates toward the closest known name, predicting print int instead. And this is our third challenge: failure to generalize to unseen yet valid patterns. Now moving to our approach, to address challenge 2 and 3, we reframe function name prediction as an image captioning problem. And in this way, we can preserve word order while improving generalization to zero-shot scenarios. And here we list 2 classic patterns in image captioning. So the first extracts image and text features separately and fuses them via a multimodal encoder and reconstructs the caption. And the second also encodes them independently, but concatenates the features and feeds them into a unified text decoder to generate the caption autoregressively. And in our new architecture for BLens, we borrow ideas from these classic patterns, replacing captions with function names and image features with function features. And our training process in general has two stages. In pre-training, a multimodal text encoder fuses different binary representations by aligning them with function names, thus enriching the representation space. And in fine-tuning, we initialize the encoders with pre-trained weights to reduce training effort and specialize the model for function name prediction. Now let's move to stage 1 combo, our pre-training stage. Our goal here is to build a unified representation that fully captures different aspects of binary functions. And to this end, we adopt an ensemble encoder combining three complementary forms. The first is palm tree, which is an assembly language model focusing on structural patterns. And then Dexter, a statistical-based embedding. And then clap, a semantic-oriented embedding. However, these representations come in very different forms. So palm tree generates sequences, while Dexter and clap output single embeddings. So inspired by vision transformers, we first convert each representation into patches by MLP layers so that they can be processed and fused in a consistent way. For palm tree, we split the sequence into patches at the basic block level. And for Dexter and clap, we project their single embeddings into multiple patches. We then add positional encodings to each form separately, since the number of patches differs across representations. And after that, we concatenate the three parts as the representation of each function. And we reach the first step, the patches, and the fusion itself is driven by contrastive learning. So the motivation is that, although the three forms describe the same function, their embeddings are not naturally aligned. So we address this by aligning patches with tokenized function name labels in a shared latent space by contrastive laws. So patches related to the same labels are pulled closer, and unrelated ones are pushed apart. On top of that, we add a captioning head to predict the function name directly, which further encourages the fused representation to retain semantic and structural information. So in short, Combo turns diverse binary representations into one unified embedding space, ready for the next stage. In fine-tuning, as mentioned before, we design a new function name decoder and name it with LORD, which is the abbreviation for likelihood order regressive decoder. And we use this decoder to predict function names from binary representations. Traditionally, generative transformers rely on teacher forcing, where each token is predicted from the ground truth previous ones, and this often makes later tokens easier to predict and weakens planning for short sequences like function names. So we instead adopt a tailored masked language modeling task, where the decoder predicts randomly masked tokens from the remaining ones. And the basic idea is kind of similar to original MLN task. For instance, here we must convert N2, and then the model tries to predict the masked words by the remaining context, hex and int. However, since function names are much shorter than natural language sentences, we adjust the masking probabilities accordingly. For a name with n tokens, we sample the number of masked tokens m from a distribution where C sub I equals 1 plus I over n for I from 0 to n, normalized by softmax. And this biases toward masking more tokens, with full masking being most likely. And thus, this scheme reduces the bias of teacher forcing toward easier prediction of later tokens. So, in the inference stage, the overall architecture remains similar to the fine-tuning stage, but we design a dedicated decoding strategy, flexible autoregression, to enhance the precision of function name prediction, and the decoding process proceeds in several steps. And in this scheme, LORD does not decode strictly left to right. To use an example for illustration, at step 1, it predicts all positions in parallel and picks the token with the highest confidence. say EOS at position 5 with 0.48 confidence, and this token is fixed, and the process repeats. But EOS token here is a special case, as to handle variable length outputs, no EOS token is actually used later. Next, int is chosen for position 3 with 0.35 confidence, then hex for position 1, and so on. So this continues until the highest remaining confidence falls below a preset threshold, which is optimized for F1 score in validation set. For instance, after predicting convert hex to int, the best remaining candidate might have confidence 0.25, which is below the threshold, so the decoding would stop here. And in this way, Lord avoids generating low confidence, potentially false positive tokens, thus keeping precisions high. So far, we've covered the core idea of BLens, and now let's move on to the evaluation. We consider two settings, cross-binary and cross-project. In the cross-binary setting, the training, validation, and test sets come from different binaries, but may still belong to the same project. For illustration, imagine using biutils. We could train on some binaries and test on others. However, in the cross-project setting, the tests come from entirely different projects. For example, training on biutils, validating on core utils, and testing on fan utils. And here, the examples are only for illustration as the actual datasets we use are different. But we introduce cross-project setting because it places a stronger emphasis on generalization and more closely mirrors real-world scenarios. So this allows us to assess how well the model transfers beyond the specific project it was trained on. We also consider different types of evaluation metrics, since each highlights different aspects and comes with its own strengths and weaknesses. So the first group is F1 precision and recall. They provide accurate token level correctness, but they ignore order and meaning. For example, convert hex to int would be treated the same as convert int to hex. And then we have blur and Fuji. They account for subsequence overlap, yet they still fail to capture semantic similarity. For instance, getInt, which is kind of semantically close to convert hex to int, would still be penalized. And finally, we have Fuzzy LR, which goes further by capturing semantic similarity. However, it may sometimes overestimate adequacy. In fact, in our table, even an empty guess received a higher Varsi LR score than some reasonable predictions. So, by combining these metrics, we can evaluate models from multiple perspectives and obtain a more balanced view of their performance. We now look at how BLens compares to baseline approaches under both cross-binary and cross-project settings. So in cross-binary setting, across all metrics, BLens consistently outperform the baseline, with especially large gains on blur. And in cross-project setting, which is more challenging for generalization, yet BLens still leads on every metric, with even larger margins than in the cross-binary case. And this slide shows a partial ablation study for both combo and Lord. So on the left part, we could see results for combo. We have a variant BLNP trained without combo, and it performs clearly worse across all metrics. This confirms combo's strong contribution to the final performance. And on the right part, we have the ablation study for Lord. Here we compare against several variants. So the first is simple, which is a standard left-to-right decoder with a confidence threshold, and then Lord T0, which is Lord without the threshold, and then simple T0, which is the left-to-right decoder without threshold, and combo, replacing Lord with combo as the decoder. So from the results, Lord achieved the highest precision, with some trade-off in recall, but overall delivered the best F1 score. To complement the quantitative results, we also present two case studies that highlight the limitations of existing metrics. So the first case on the left, the ground truth function name is execute, while BLens predicts shell. Although the prediction is marked as incorrect by standard metrics, the two are clearly semantically related, and this shows how some meaningful predictions are not properly captured in the reported scores. And we have the second case on the right. The ground truth name is task panel cancel clicked CBK, and BLens predicts on button cancel clicked. Here, BLens not only provides a semantically correct label, but also one that better aligns with common naming conventions. So this demonstrates BLens' ability to generalize patterns from other projects and produces more formalized names. And together, these examples illustrate that BLens can generate high-quality predictions that go beyond what the evaluation metric reflect. In summary, BLens offers a multimodal learning framework for function name prediction, and our approach achieves state-of-the-art performance with 92% precision, substantial improvements in fluency, and strong generalization across Ensemble projects. So that concludes my presentation today. I'll be happy to answer any questions via emails. Thank you.